Let's try Y source connected to delta load. Sometimes you encounter like a Y source to a delta load or a delta source to a Y load. We like to see them Y to Y or delta to delta. So let's take an example. Let's say we have a Y source, and I'll give you some numbers for it. I'm just making this up. I have no idea. This is 120 angle 0. This is A, N. This is B, so VBN will be 120. We'll say it's a positive sequence. That's negative 120 minus the plus. And this is C. And this is VCN, which is 120 negative 240. Now we're going to connect this to a delta. Balance delta load. Pick a value for the load. What do you want to have that impedance here? And it's not just resistor. Let's get an impedance there for it. 3 plus 7J. I'm just making that up. And this is A, this is B, this is C. So when you connect them, A is connected to A, B is connected to B, and C is connected to C. The problem here is when you're watching the current, this is A and A, this current here going in, we'll call it I sub AA, the line current, it's not the current going through this one. It's going to come down, it's going to split. So that makes the math not really fun to do, because you don't know what the current they are going through it. I can do one of two things. I can either convert this to a delta source or convert this to a Y load. And if you want to convert a delta load to a Y load, we go back to circuits 1. I just went through the drawer when I was looking here, and I pulled my notes from last semester. Delta to Y. I saved that page, knowing I'm going to need it. And this is when we dealt with just the resistors at that time. If you have delta, you want to convert that to Y. This resistor here, it's the sum, the product of these two over the sum of the three of them. This resistor R sub 2 is the product of these two over the sum of them. And this resistor, the product of these two over the sum of them. Well, that doesn't change here when you have Z's, so we'll call them Z delta and ZY. So we'll make our own now. We'll call that Z delta. We're assuming these are equal. If they're not equal, no big, you know what? Let's not assume they are equal. If they are equal, we'll just make that the case at the end. This is Z1, Z2, Z3. In our case, they are equal for that example, but I'm going to give you the equation in general there. I'm going to find the equivalent Y value of that. We'll call them ZA, ZB, and ZC. Just like the resistor here, ZA is going to be the product of these two. Z1 times Z2 over the sum of them. ZB, that's this one right here. is going to be the product of the two adjacent one, which is Z1, Z3, over the sum of them. And ZC, that's this one, the product of these two, Z2 times Z3 over Z1 plus Z2 plus Z3. Well, if these Z's, Z1, Z2, and Z3 are equal, if they are equal, we call them Z delta. So what you're going to have is Z delta times Z delta, that's when it's balanced, over what? 3 times Z delta. And this cancels that, you end up with Z delta over 3. Z delta over 3, and this will be Z delta over 3. If they are balanced, if the load is balanced. If it's not, then you got to do it this way. Find the value for each one. So to find the Y value, we divide that impedance by 3. And we can do vice versa. We can actually do from Y to delta. If you have the Y value, which is ZA, ZB, and ZC, if you have these values and you want to find the equivalent delta, I'll use what you're finding in red here. Z1, Z2, Z3. Just like the resistor we did here, remember the resistors? We said if you want to find this value, you go this times this, plus this times this, plus this times this over the one opposite, which is this one. So if I want to find Z1 here, it's going to be ZA times ZC plus ZC times ZB plus ZB times ZA over the resistor or the impedance opposite to that, which is ZC. Z2, the top is always the same, A times B, or A times C, C times B, B times A. If I'm looking for this, I'm going to divide by that resistor, ZB. And if I'm looking for Z3, that's this one. Again, the top is the same, ZA times ZC, plus ZC times ZB, plus ZB times ZA, over ZA. And if all these values are equal, this will be ZY times ZY, that's ZY squared, 3 of them. 3 ZY squared divided by ZY, what are you going to have? 3 times ZY? So that's 3 times ZY. That's 3 times ZY if they are equal. So if you have Z delta and you want to find ZY, you multiply it by 3. If you have ZY, you want to find Z delta, you divide by 3. If they are equal. So here we go. ZY equals Z delta divided by 3. And this one says Z delta equals ZY times 3. If they are equal. So going back to my problem, here we go. Maybe I will change this one to a Y load. That's delta to y. You divide by the square root of 3. I mean, divide by 3, not square root 3. Let's divide each one by 3. So if you divide it by 3, you can take that problem now and rewrite that, make it look like this. A, B, and C. And you can take that load now and you can change it to a Y load. Capital C, capital A, capital B. A is attached to A. B is attached to B. C is attached to C, and N is attached to N. And what's the value of this? It's going to be 3 plus 7j divided by 3. Whatever the delta value divided by 3. So let's divide that by 3. 3 comma 7 divided by 3, and the value of each one is 2.54, angle roughly 67 degrees. 2.54 angle 67 degrees. 2.54 angle 67 degrees. And now you can just draw one face, because if you travel along one path, let me get a marker here, highlighter. If I take a one loop here, N to A, and continue with it, this is my closed loop right there. So if I draw just one of them and try to analyze that, I will have this circuit. .54 angle 67 degrees, and this is capital A, capital N. Can I find the current I sub AA now? I sub AA is going to equal to 120 angle 0 divided by 2.54 angle 67. .120 divided by 2.54 angle 67 degrees. And the current is 47.24 angle negative 67 degrees. And I know what I sub CC and I sub BB. Subtract 120 from that. Minus 120, that's negative 187, is it? And what's I sub CC? Subtract another 120 from that. Is it 207, 307? So once you change it to Y, then it's straightforward. Y is much easier than delta. Much, much easier. So you're going to see us always trying to convert that load to actually a Y load. I could have converted the source to a delta source, but the math's still going to be a little bit ugly there. I can find the current through that. I mean, I can do it, and I'll show you that in a second. Now, if I want to find the power delivered to the load, what's the average power? Yep. I need to know what R is. That load here, if I change it to rectangular instead of polar, remember it's 2.5467. That's 2.54 cosine of 67. Cosine of 67, which is what? 0.99 plus j 2.54, the sine of 67. J what? 2.34? So the average power delivered to the load, it's I squared R. I is 47.24. Square it. Then you multiply it by R, which is 0.99. The average power delivered to that inductor is 0. 47.24 squared times 0.99. It's 2209 watts. That's per phase. The total power to the load is going to be 3 times that number. 3 times 2209. Which is 6627.9. I'm carrying all the digits. Watts. That's the average power delivered to the load. What is the power factor? For the source, the load doesn't matter. There's nothing else between them. It's cosine theta v minus theta I, which is cosine theta v, which is 0, minus theta I. What was theta I here? I forgot what that current was. 67. Was it 67 degrees? Yep. Minus the 67. Negative, so minus and minus will be a plus, right? Minus 67. So theta v minus a minus 67, that's plus 67. Notice that's a positive value, which means lagging. It's an inductor, has to be lagging. What's cosine of 67? Not a good actual device. We're getting 39% of the power delivered. That's all we're getting. Now, I could have done the problem a bit differently. Instead of converting this to Y, I could have converted the source to delta. That's another option. So here, the first option, I said, let me make this Y. Y to Y is much easier than delta to delta, but I'll do it the other way. So the same problem. Same problem. But I'm going to do here is convert the source to Y. I mean source to delta, not Y. It's already in Y. This is my circuit. I'm going to convert that to delta. If I convert that to delta, I'm going to have a delta source now. And that's going to the delta load. Here we go. Three plus 7J. 3 plus 7j, plus 7j. This is A here. So this A will be attached to A. This C will be attached to C. And this B will be attached to B. Like that. And what are the values here? That's the line voltage. So my VAN was 120 angle 0. My VAN was 120 angle 0. So what is my VAB then? I'm going to multiply it by the square root of 3. And I'm going to take this angle and add 30 degrees to it. If you remember the math. We multiply by the square root of 3 and we add 30 degrees to it. So what is square root of 3 times 120? .208 roughly. Angle 30 degrees. So 208 angle 30 degrees. This is 208, subtract 120 from it. What's 30 minus 120? Is that negative 90? And this one, 208, subtract another 120 from this, negative 210. Now let's trace one branch here, one loop, A to B. This current going through this, A to A, it's not this current. This current is going to come down, split into two currents. KCL. Kirchhoff current law. The current entering the node is going to equal the current leaving the node. So what is that? What's going to happen? Now we're dealing with delta to delta. I can tell you what that current is. I can tell you what this current is. Why? That's in parallel, looks like that voltage source here that you see it, it's crossed this one. So I can actually find I, A to B. Coming down, that's this one. It is equal to what? VAB divided by Z between A and B. The voltage here is the same voltage right here. That's what? 208 angle 30 divided by, what's the current here? I mean, what's the impedance here, not the current? 3 plus 7j. So let's do the math. 208 angle, 208 angle 30 divided by 3, 7. That's 27.31 angle negative 36.8 degrees. I know what I sub B to C is. I sub B to C, that's this current. It's the voltage here, so it's going to be the same as this, except subtract 120. Negative, what is 36 minus 120? Is that 156? And I sub C to A is going to be 27.31. And subtract now another 120 from that. negative 276.8. If I'm doing it right, 240 and 276.8.
So is that rule earlier for converting with just 3 times Z, that's just for impedances? You can't do that with a...
That's correct. That's for the impedance. For the source, you multiply by the square root of 3, or you divide. Depends if you're going from A to B, or, if you have a VAB, you want to go to VAN, you divide by the square root of 3 and you subtract 30 degrees. If you have VAN, you want to go to VAB, you multiply by the square root of 3 and you add 30 degrees to it. The question is, we said for the impedance we divide by 3, but for the source is different. For the source, if you have VAN, and I'll give you some number, let's say V max, angle theta, you want to find VAB, you multiply it by the square root of 3, and you take theta and you add 30 degrees to it. So if you go from this to this, if you want to go from this to that, we divide by the square root of 3 and we subtract 30 degrees, the reverse.
Okay, so you can just initially subtract 30 degrees and then subtract 120 and 240 from the other two? Is that
We could, to get these numbers, that's what I did. I subtracted, I get what?
No, I meant for the first one, you know how you add 30 degrees?
Mm-hmm.
Would you be able to subtract 30 degrees and then keep the other two balanced by subtracting 120 and 240 again? Or would that mess up the math?
I'm not sure. You subtract 30 to get this number, that's what I did. Or you add whatever the case is. In this case, I actually added 30 to get that number.
Right.
Once I get this value, just add 120 to it to get this, or subtract 120 to get that number, and subtract 120 to get that number.
Right.
That's what I did. Now, can I find the current from A to A? If I do KCL, the current entering the node, I define A to A, the current going that direction. Based on my picture I drew there, it's from A to B. The current entering the node, which is this one plus that one, equals the current leaving, which is this one. So if I do KCL at capital A here, KCL at capital A, sum of the current entering the node going into the node should equal sum of the current coming out of that node. What is going to that node? I sub AA plus I sub CA, from C to A. What's leaving that node? I sub A to B. So what's I sub A to A? It's I sub A to B minus I sub C to A. Mathematically. Do we know what these numbers are? A to B happens to be what? 27.31 angle negative 36.8 minus I sub C to A, which is 27.31 angle negative 276.8. Let's see what that number is. I'm really struggling with the calculator putting numbers in it today. But I got 47.3 angle negative 66.8. This is the current from A to A. Was that what we got earlier when we did it? When we converted the load, was that the same answer? I sub A to A, 47.24, angle negative 67 degrees. Same answer.
Basically just do Y to Y.
So notice the YY was much work a little bit delta to delta, a little bit more work. Now, if you want to find the average power delivered, we calculate the average power delivered to the load. When we convert that to, we said per phase was 2209, combined 6627.9. So let's look at it. I know the current through this. That's A to B. So I can tell you what the average power absorbed by that impedance. So P average for the 3 plus 7J is the current through that square. What's the current through that square? It's I sub A to B. I sub A to B. What was my I sub A to B? 27.31. The current was 27.31. Squared times the resistor, which is what? 3. That's per phase. Let's do the math. See if that number 2209 is somewhere in that neighborhood. It's 2237.5. For 3 phases, the total power three times 2237.5, which is 6712 watts. Now again, when we did it the other way, 6627, so I'm off by about 40 watts, but I'm sure that's rounding errors. Just like that number, 47.3, they got 47.24. When you square it, yeah, the errors start to magnify much faster. So that's why the difference in them is supposed to be 2209. I get 2237. So you have two options. You can convert the load to Y, which will be easier, or you can convert the source to a delta and do it. Either way, your answer is not going to change. If you carry a few significant digits or a few decimal places, your answers will be on the money. Joe, go ahead.
On the test, are you going to make us like do one of
I'll let you decide. No, logically, probably this is the easier to convert that. But if you decide you like the hard way of doing it, then go ahead. You know. So this is really why I did two sections. I did Y to delta and delta to delta in this example. You get to see how delta to delta work. You know.